Hello, this is like take 5 or something. Yeah, very unscripted content. So today I want to talk about panics in Rust, particularly pertaining to FFI, because a few people at work have been kind of struggling with understanding this, and people have been making mistakes regarding this, so I really wanted to just clarify how this all works. It is a very confusing topic, and it doesn't help that the state of panicking across FFI boundaries, or at least unwinding across FFI boundaries, has changed quite a bit in the last several months. So we're going to dive into some history, and then I'm going to start showing you some examples of how things have changed and how C and C unwind as ABIs differ. So if you look at panicking across FFI boundaries in Rust, you'll see that there's a lot of links here that talk about how panicking or unwinding across an FFI boundary is very much undefined behavior. You can kind of see that here. If you panic across FFI boundaries, you'll trigger UB. So this has caused a lot of people to think that, oh, if I, am writing a Rust library that I want to call from C or Java or Go or Python, right? If that Rust library ever panics, right, then that's undefined behavior, and that's very dangerous. Oh no, that's terrible. And that was actually the case for a while. But, well, unless you did something particular with the panic runtime and made it abort. But basically, if you ended up unwinding across this FFI boundary, that was actually considered to be undefined behavior. And it still technically is. It is undefined behavior to unwind across an FFI boundary. But some cases have been defined, right? If you're using the somewhat new-ish C unwind ABI, which was stabilized in version 1.71 of the compiler, then you are allowed to unwind across FFI boundaries as long as you use that ABI. However, if you're still using the extern C ABI, that would still lead to undefined behavior. However, in version 1.81.0 of the Rust compiler, you can see from here that uncaught panics in these extern C functions will now abort. So now we no longer unwind across that FFI boundary. Now we're actually just aborting. So it is now safe to panic in that Rust library that we're trying to call from our foreign language, right? So that's what this change is about, and this is something that a lot of people aren't really aware of, or they just don't really understand. We've also got this RFC here with this table trying to explain all this, but a lot of people don't really understand. They get kind of confused, especially by the panic runtime. So I'm going to try and show off how this stuff all works. So we're going to come over to our terminal here, and just to show you what version we're on, we're using Rust C 1.82.0. Now, I just want to quickly clarify that on newer versions of Rust, particularly Rust C version 1.85 and newer, you're going to probably be using Rust Edition 2024. That's the newest Rust edition that came out, and it's only available on Rust C 1.85 or higher. So in this particular project, we're going to be using Rust Edition 2021, so the code might look a little bit different. This repo that I have here has an updated version of all the code that will work on the latest edition. So if you are using the latest edition of Rust, then you can take a look at that as a reference. But otherwise, I'm just going to stick to the 2021 edition syntax. So here I have a couple of projects. I have panic lib and panic bin. So these correspond to our Rust library and our foreign language. So if we have, like, say, Java code trying to call into a Rust library, the Java code would correspond to the panic bin, and the Rust library would correspond to panic lib. Now in this case, I'm not using a different language. I'm just going to use Rust on both sides, but because we're using the C ABI, it doesn't really matter. If we compile this panic lib, it's going to turn into a .a file, and so the panic bin doesn't really know or care what language that .a was generated from. It could have been generated from a C compiler. It doesn't really know, but because it's using a C ABI, that doesn't really matter. So yeah, I'm just going to show you what I did here in the panic lib first. So I'm going to actually run cargo clean here to make sure that we remove the target directory. I was doing some tests earlier. So if we look at cargo.toml, you can see that our crate type is static lib. So we will generate a .a when we compile this. And when I look at the source code, we'll see that we've defined two functions. One is an extern C function, and one is an extern C unwind function. So like I said, two different ABIs, two different functions. If we come to panic bin, we'll see that we have this custom build script. This lets us link in the library that we defined earlier. Actually, let me just go and quickly build that before I forget to do that. There we go. And we'll look at cargo.toml in our bin, and we'll see that there's no dependencies because, again, we don't care that this was compiled in Rust. We don't know that it was compiled in Rust. It's just a .a file. So the compiler doesn't have any hints there, so we don't need to specify any dependencies. And if we look at the source code, here's what our source code looks like. We define two extern blocks which declare our C ABI panic and C unwind ABI panic functions using the C ABI and the C unwind ABI respectively. And then here we're going to try to do a catch unwind, as we call C unwind ABI panic. And then we're going to print panic occurred if there was a panic. Now, if you're very astute, you might realize that I'm doing something very bad here, but I'm going to gloss over that for now for pedagogical purposes, and we're going to just pretend that this is totally fine. I'm not doing anything wrong. We'll talk about that later. So if we run this code, we'll see that we get this panic occurred message to print out here. And it'll give us the cause, which is just any, and well, that's just because I just did a very generic panic. But yeah, this is what happens when we try to call C unwind ABI panic. And if we try to call C ABI panic, let's do a cargo clean to make sure that we rerun the build script. We're going to run cargo run here. We're going to get a very different output. So we're going to actually see this big old backtrace here. And so this is something that was confusing to a lot of people on my team, and I really want to just clarify what's actually happening here. So what's happening is, because we're on this Rust C version 182, what's happening is when we panic in the library code, it hits the FFI boundary and then it aborts. So you can see that we never printed this panic occurred message or anything. We never actually hit that catch unwind. We never caught the unwind in our application code. And of course that's because we panicked in the library code before, or we aborted rather in the library code before we ever crossed that FFI boundary. So this panic doesn't actually unwind into the panic bin code. So that's why we never actually see that stuff. Now, what you will see is that it does actually collect a backtrace. So that's very useful. But this is something that was confusing people because it made people think that, oh, it's unwinding, right? Like, if it's not unwinding, then where is it getting a backtrace from? Well, this is where panic runtimes come in. So if we come to panic lib over here, I don't know why I did that ls, but if we come here, we can see that we don't define any panic runtime. And if we look over at the documentation for profiles in Cargo, we'll see that for a default dev profile, which is for debug builds, which is what I'm doing with Cargo build, and also for release, we'll see that the default panic runtime is unwind, right? Same here. Default panic runtime is unwind. It's not abort. So what that means is that when we panic, we're actually unwinding those panics. We're actually unwinding the stack up until we hit that FFI boundary. Then we abort. So this is actually doing some amount of unwinding. We can actually change this if we do profile.dev and we set panic equals abort just to prove this, right? So if I rebuild this, I'm just going to do a cargo clean just in case. Cargo build, come back to panic bin, and we'll do a cargo clean, cargo run. And we'll see that now it aborts without a backtrace. That's because we're not collecting a backtrace at all anymore. We're just immediately aborting when we hit that panic. So that is the difference between the panic runtimes and the C ABIs. Okay, lastly, I wanted to just show off what happens on an old version of Rust. So we're in Rust C 1.73. This is what after 1.71. So C unwind does exist, but we don't have the abort when unwinding across FFI boundaries. So let's go to panic lib. Let's define what our runtime is going to do here. So it's going to unwind. Okay, that's the default behavior. We're going to do cargo clean, cargo build. We're going to go panic bin. We're going to define this not to abort. We're going to edit our code here to call the C ABI panic. So if we cargo clean, cargo run, we're going to see that we get this panic occurred. So yeah, that's showing that in the older version of Rust on 173, yeah, it unwinds despite the fact that we are calling the C ABI panic, which is not C unwind. So that was considered undefined behavior. The fact that it managed to unwind across that FFI boundary without using this C unwind ABI is not aborting. Okay, so now that we've looked at some code examples, I just want to go over how we can avoid undefined behavior. So if we look at this chart here, we can see that we covered this entire column. So this is when we write a Rust library that we want to call from another language, like C or Python or Java. It means that no matter what we do, if we panic in our Rust library, we're not going to encounter any kind of undefined behavior because in every case, no matter what panic runtime we use and no matter which ABI we use, we're either going to safely unwind across the boundary or we're going to just abort, either at the FFI boundary itself or directly at the panic site. So now we talk about this final column here on the far right, and this is where things get a little bit nastier because here there are actually some cases where we can encounter UB. So what are these cases exactly? Well, basically it's any time you try to unwind from a foreign library into Rust code. So that's like when I declare that extern C block in my Rust code to declare that I'm going to call this foreign function C ABI panic, for example. So anytime you try to call into an extern C function from Rust, if it unwinds into the Rust code, that is considered to be undefined behavior. So it's okay to do this if that foreign function doesn't unwind into it. And so in our case, where I was showing off this panic lib that was written in Rust, because it aborts in this case, right? It doesn't actually cross the FFI boundary, and therefore it doesn't actually trigger undefined behavior on the application side. The binary application doesn't have to worry about the panic propagating through it because we abort before we ever reach the application side. So that's kind of how you avoid undefined behavior, is you just avoid this C ABI whenever you're calling foreign functions from Rust. So if you want a useful mnemonic to think about it, if we just boil it down to these two columns here, the left column here is the library case when we're writing our Rust library. These are the cases you have to consider. When we're writing our Rust executable, these are the cases that we have to consider. When we are consuming, when we are calling a foreign library, this is the case that we have in mind. So left column library, LL, and if it's not on the left, then you have to worry about it. It's this column. Now there are some interesting exceptions here, and one thing that I want to just quickly show off is how unwind works here. So I talked a little bit earlier about how I was doing something very bad in my code, and of course that thing is this catch unwind. So this RFC does not define the behavior of catch unwind. So this is actually still an unresolved question. It's something that the project group would like to specify in a future RFC, but catch unwind's behavior, when you unwind from a foreign function into your Rust code, that is actually undefined behavior. So if you try to call a C unwind function, for example, and so let's say that we're using the unwind panic runtime, we've declared the function to be C unwind in panic lib, and then we unwind into our Rust application, into the panic bin, the binary, the application, then it's still going to be undefined behavior if we use catch unwind. So we have to be very careful about that. If we use catch unwind, that's going to be undefined behavior no matter what. So you're probably wondering, well, what is the use of C unwind? Well, the guide level explanation actually tells you all about it. So it's useful in these cases where you want to sandwich your Rust frames. So I've kind of drawn it out here, but let's say we have C++ code that calls into Rust code, and then that Rust code calls into C++ code. If this C++ code starts unwinding like this, it is not legal to try and do a catch unwind here. And in fact, we have to use C unwind here because remember, if we declare this C code, or C++ code, sorry, as extern C, that's undefined behavior, right? We're unwinding from we're unwinding from an extern C function into Rust. We're unwinding from a foreign function into Rust. That is not allowed unless the ABI is C unwind. So we have to make sure this is declared as C unwind. However, because catch unwind is undefined behavior, we can't catch it here. We can't handle that unwinding from the C++ code here in the Rust code. So we have to actually propagate it up to the C++ code that called this Rust code. And so that's what specifying C unwind does. And they also mention that you could just use the default Rust ABI, where you don't specify this ABI string at all, right? Or you can then use extern Rust to do it explicitly. But essentially, that's the purpose of using C unwind. It's to just propagate up these unwinds in case your Rust frames end up getting sandwiched between the frames of another language. So this is why you want to make sure that you're actually not using catch unwind in these cases. And maybe there's a case where maybe there's a case to be made for catch unwind being used, like for example in my case where I was using a Rust library and calling it through a C ABI from a Rust binary, but there isn't really much of a real use case for that. Like I can't really imagine why you would want to do that in like production code for any like real project. Like why, if you're gonna call Rust from Rust, well, you might as well just use Rust, right? You might as well use like the Rust ABI. You might as well use like rlibs and regular dilibs instead of like C dilibs, right? Like there's no real point in doing that. So there could be an argument made there that maybe that should be like considered defined behavior or something, but like it's kind of an unrealistic case. So what we really care about is when we unwind from a foreign function into Rust. And they do specify unforced foreign unwinds. They talk a little bit about forced unwinding here. It's a kind of a special case. I don't want to get too into that. If you want to learn more about that, I would recommend just reading the RFC, reading these posts on your own time. But yeah, that's pretty much it. I guess I should also mention that in these cases here, when we're talking about this far right column, in this case, the panic runtime here is referring to the panic runtime of the application. So when I was showing off my examples earlier, I was setting the panic runtime in the panic lib in the library. But of course, when we're calling foreign functions, they don't have a panic runtime. They might not even have a concept of panic, right? Like C doesn't have this panic notion. So when they talk about panic runtime in this column here, they're actually talking about your application code, the code that's consuming or calling into this foreign function that is unwinding. So if my panic bin, for example, had the panic abort flag set in its cargo.toml, then if I were to call an extern C function, or in this case, sorry, an extern C unwind function, then it would abort. And so in my case, I can also maybe just quickly try and show this off here. All right, so if we come to panic lib, let's make our panic lib actually unwind. It's already unwinding, that's good. So I'll do a cargo clean, cargo build. We'll come back to panic bin. We're gonna set this to abort. And look at the code here real quick just to make sure what we're doing. Right, so we need to call C unwind ABI. So if we call C unwind ABI panic like this, then when we do a cargo, let's do a cargo clean first, cargo run, you'll notice that we get this backtrace still, and that's because, like I said earlier, we're still collecting a backtrace because we're unwinding in the library. We're unwinding until we hit that FFI boundary. Now, in this case, we're actually unwinding past that FFI boundary because we used C unwind, but that backtrace is still part of that panic. So when we receive the panic on the application side, we still print the backtrace here before we abort. So yeah, you can see that we're aborting now. We're not printing any messages about how we received a panic or anything else like that, like I had in the actual code here. If you look at this match case here, right? Like we have this panic occurred thing. That panic occurred message didn't print, so therefore we know that we're actually aborting before we get there. And so that's why we see this abort case in this column here. And of course, if we wanted to specify the default runtime, we would see an unwind there. I can show that off. So if we go to cargo.toml and we just delete this, like so, cargo clean, cargo run. Again, now we unwind instead. So we catch the unwind and then we print this panic occurred thing instead of aborting.